first slide. Okay, see whether you guys can spend some time thinking about it. So what happens is there's this function, and there are some caller save registers and some callee save registers. And some of those registers I just did a very abstract way used. And then there's a function call, and at these 4 locations you have to either save and restore some stuff, which has to be saved and restored where. Which has to be saved and restored where? Which registers? So, what should happen at the top? Which one?
S0 after S7.
Do you have saved everything? What will we use? Because what I have to save is the things I actually use.
0 after 2.
0 and 2, I have saved. Where do you restore them?
Variant.
Variant. Okay, next one is a little bit more interesting. Before call to bar, what should I have to save? Anybody?
T1. And
T1. Anybody think T0 needs to be saved? And T2? Why? Exactly, the value is not live. The only thing you have to save is if the value is live across that function call. The value is not live. So basically what happens is you saved and restore T1 here. You have to save and restore all the SS used in the function basically. Okay, so last time we went very fast over the procedure linkage, and I'm going to go a little bit slower this time and go through this. This is the second time, so if you have any questions, ask me. Then I will talk a little bit about code generation of statements and control flow. That kind of covers everything that's required, and a few slides on the architecture you guys are using, and give a little bit of overview of different type of architectures out there. And then finally, some guidance of how to write a code generator, so you guys can get started. By the way, did Punya give you the account information to get into the x86-64 machine? No? Okay, so we'll try to get it today because we created a bunch of accounts for you guys and get started fast. So that's the first thing. Procedure linkage. So what happened is, every time you do a function call, procedure call, you have to do a pre-call. There's a prologue and epilogue at the caller side, and also prologue and epilogue at the callee at the beginning and end. So let's go through what this changes from every architecture to architecture. In fact, what we are giving for decaf is in fact not the calling convention for Linux x86-64, which seemed to be a little bit too complicated. So we created a smaller, simpler calling convention. So what that means is, if you directly call a Linux library, it won't work. Or if you compile another object, a Linux object, and then link them together, it won't work. So you need a little bit of a wrapper. So this is a simpler calling convention. So what we assume is, I have RCX is live, and so I have to call a save that one, and I am passing calling foo with 3 different arguments. So these are some I just said where they are in the stack. basically, because they are local variables. Some are sitting in the stack. We know those things. And so what we have to do is, so when you start, we have a stack like that. We have a dynamic area, something might have push, stack temporaries, local variables, call save registers, all those things are in the stack. And most of these are accessed through the base pointer in here, or the frame pointer. So what the first thing you have to do is, you have to save these call save registers. Either some fixed location you put it there, or you can just push it and if you do a matching pop at the other end. And then I need to put those arguments in there. I push those arguments into the stack. You can do this by just doing push and pop. Also, if you actually calculated the stack location, you can do explicit saves of base pointer. But pushing and popping is probably okay. That's right in there, because if you're doing base pointer, that means you don't have, if you have multiple function calls, then you need to have an exact same size frame, which is hard. So each function you push what's needed. And then I do the call. Call instruction by itself will go and put the return address in there and get the stack will point there. So now I am at that point, I actually am in the callee. And assume the callee has one register that is basically callee save. So the first thing they called, and it needs 40 bytes for locals. So what first thing I had to do is I had to push the frame pointer, because I am starting a new frame, so I had to store the old frame pointer. And after I store the old frame pointer, what I do is I update my frame. Now everything is out of the new frame in here, my new function. And then I added 48. Why 48? Why not 40? I'm trying to resave this callee save register too. I have 40 for all the locals, but I had to put the callee save register somewhere too. So basically what I did was I added in room for callee save registers. Stack temporaries I don't seem to, and local variables require 40 bytes, so I added that. And I have 48 bytes, and I do that, and then finally I move the callee save of the frame pointer in there. So now I'm ready to do what the function has to do. So what kind of things you do in the function? Oh, by the way, so all those things can be done by one instruction called enter. So you can use either. Enter is easier to generate. So the next thing is, now I insert in the function. Now I can access all my parameters using basically what we did. So we pass parameters by just pushing them into the stack. So we know where the arguments are in there, just before the return address in there. And then when I want to address, I know exactly that from the base point to the offset. The first one is 16 off there, because there's you have to pass the return address and get to that. And then you can just do moves, save, store of that. Okay? So it's pretty easy thing to do that. So all the arguments that get passed is accessed directly off base pointer. That's great. And then locals also you are addressing on the other side of the base pointer. So locals and temporaries, you probably have a map somewhere saying where those things are. You allocate memory, and you can just directly go and access those things. So now, by doing this, you know how to access both the locals and temporaries, what you assign, as well as all the arguments. So now we are here, ready to return. So what do you have to do in return? We have to restore the caller save register. So we basically restore that thing in there. And then one convention we follow is all the return goes through a register. We don't put return value in the stack. So return value goes through the register RAX. So what that means is you copy the return value into RAX. Assume this return value was here in a local here somewhere. We copied it to RAX. And the next thing you do is you restore the stack pointer. Why didn't I just go? I did before, and I did a subtract 48. Why didn't I go and just add 48 to RSB? Why did I actually copy RB PP RSB? What happens if I just, because before and I did was I add 48. Why did I just go and do subtract 48? Would have done the same thing? Anybody want to take a guess? Is it too early in the morning? It's not that early.
It would have worked if you had popped something onto the stack or pushed something onto the stack and then never bothered to pop it out.
So if you had messed up your stack in the function, because you are going through control flow doing different things, and if you messed up your stack, and the minute you subtract something thinking the stack is a certain way, you just function is gone, and you will never return out of it. You'll crash in the program because you just this thing's return address somewhere here. By doing this, at least even if you have messed up your stack, you can recover because that value didn't change. And so that's a nice thing to do basically. So this gives you much better chance of recovering from some kind of a mess up on the stack. The stack you keep pushing and popping a lot. So the next thing is you move the frame to the previous one, and I return. And voila, I'm out of this function. So at that point, also these two instructions could be replaced by leave. Again, this is a thing about x86 basically. Everything has its own instruction. And it's amazing how complicated things some of these instructions does. So Punya gave you that, but I want to actually show exactly what these things do. Now I'm coming out of the call. First thing I want to do is I want to get rid of all the arguments I passed because I actually pushed them. So I can either pop the same amount, some, and get rid of it, or it's easier just to add to the stack pointer in there. And I save this register. I need to restore that register, and then also I need to move the return value I got to wherever it's supposed to go, because normally we keep all the values in stack or global storage. You don't keep things from registers, so we move it from there, and then you are done. So at this point, we know how to do a procedure. So by doing this, generating this code, you should be able to basically call a function, come out of a function, and also generate the prologue and epilogue for a function. So you should be able to get to that point. So most of things are there. So let me go through a simple example to demonstrate this. Something decaf looking program. There's a function down here that do a comparison and basically trying to find basically to find the difference, basically absolute value of the difference, and then add some value into this one. And then so what I'm doing is I'm passing three global values into this one. So what that means actually. Not globals, actually three locals from the function main. So locals, I have this kind of a frame pointer starting. So px, py, pc is in the local variables in here. And then I'm here, and this is what my stack will look like. And the minute I call, what happens is, before I call, I basically pass the arguments. I put the three arguments in here, 10, 20, and 30. Still, I don't know what names it's going to bind to because I haven't actually done the call in here. So the minute I do the call, I'm here. I actually got the return address and frame pointer going in there. And now I know which arguments match up. Basically, cx, bx, ax get matched up here. And then now, when I go into this function, I actually will allocate my dx, dy, dc also in here. And voila, I get basically now I can go and execute what's inside this there. Okay, so another question. Why do I need the base point or frame pointer? Why can't we just use stack point and use that register for something better?
Well, you can just keep track of where the cycle is.
Yeah. So what that means is, or the way we are accessing locals and basically parameters passed is off the base point. A nice thing about that is within the function, those offsets are all the same. But if you are doing it stack offset, every time you push something, that all the offsets keep changing, so you have to actually keep tab of where stack point and where all the offsets are. Can be done, but could be quite messy.
I guess the other side of that argument is that the compiler, like that's all done by the compiler. So the compiler is going to get very good at tracking things, and you don't use the base points, so you can extra register these, which is, I guess now it's just fun the system coordinate. Very good.
Yeah. But the trouble with that is sometimes if you throw exception, the system relies on base pointer to figure out where the stack frame is and stuff like that. If you're messed up with the base pointer, you just did a divide by 0, and now it's completely no idea where you are in the stack, and then it's hard to kind of undo things. So base pointer gives some advantage because it gives a very clear indication where each frame is. So things like recovering from exceptions and stuff like could be very much easier to deal with. Otherwise, you have to go make some assumptions. Just scan and say, okay, I think this is the return address. So, okay, at this point, we have covered most of things that's necessary to do the code generation. And the two things that's left is control flow and statements. And we'll go slowly cover control flow and statements. At that time, you guys are ready to go write a full code generator. So, generation of statements. So, normally the thing about statements is they have expression trees. And statements are either just an expression tree that get evaluated by a compare instruction that change a condition code used somewhere else to do a branch, or it actually is evaluated and assigned to some variable. There's one thing that can be a little bit more complicated. Anybody can say what it is? That is if you are assigning it to array access. So then the left-hand side is not simple variable. You actually have to calculate address too in some sense. So it's not a simple going into one location. So you might have some address calculation coming up there too. So that means the top is a move with some address calculation coming. So the key thing about this is how to arrange evaluation order of expression tree. And we have to keep all the intermediate values. Those are the two things we have to decide. And we will do some very simple, dumb things. And there are two approaches, the stack model and like a flat list model. So in the stack model, what you do is very simple. You look at the expression tree, and you start emitting code in a recursive way. You can first say emit the code for the left subtree, emit the code for and put the results into the stack, emit the code for right subtree, put results into the stack, and then generate an instruction after all those instructions are generated that say take the two things from the stack, do the operation, and put the result on the stack. It's a very simple stack machine. So if you do that recursively, very simple recursive call, and at the end of the day, what you'll have is a piece of code that basically push into all the intermediate value into the stack, calculate, and return come in there. The thing about this is it's pretty inefficient. And more than inefficiency, when you go to code optimization, it's a pain because things are in stack. You have no idea what order things get in, and things become much more complicated to optimize a stack machine. So we can actually go with a flat list model. Flat list model is also something similar. What you do is you want to flatten out all the expression tree. So what you do is you do left to right depth first traversal of the expression tree, and on the return of the traversal you start generating code. So what happens is at every expression, so you have operation. What you do is you put that result into a temporary. And then when you come from then when you come from expression, you'll have two temporaries instead of two operations coming in there. And you take the temporaries in there and operate, do the operation and put it into temporary. And then at the end of the day, you have a straight line list of things that have a bunch of temporaries. Here's one thing I'll tell you guys. Don't try to do anything crazy with temporary. Every time you need a temporary, allocate a new temporary. And you go allocate a new temporary. Don't try to do reuse temporaries, none of those crazy business. Why? Why am I saying that? Why don't you want to try to reuse temporary?
Later the optimizer is going to get past that actually figures out where it is.
Yeah, so let it leave the optimizer doing that. So another interesting thing is, so assume I come up with this rule saying, okay, by the way, each expression is evaluated separately. So what I'm going to say is I'm going to use the same temporaries for each different expression. Sounds great, sounds simple, it will work. But then what will happen is when you go to optimize, you say, wait a minute, I want to move these two expressions around. And now when you actually try to do analysis, it looks like it has all these dependencies because it's using the same temporaries. And now you have to know that, okay, by the way, if it is a temporary, it's not dependency, other one, so it gets too complicated. So if you have separate temporaries, things become easy. And nice thing about you, optimizer will actually generate faster code. You can actually see it faster. So start dumb and speed up.
Can you give an example of the flat list model?
So we'll say something like this. So what you do is, what you want to generate is do this one. So say move. I'll just say A. Okay, I'm not saying that. We'll say R10 move B to R11, and then say move sub R10 R11. We'll say put it into R11, and then what I will do is move R11 to something. We'll say minus 24 out of. So this is where this temporary goes. So I mark here, I am a minus 24 out of RSBs. This is where this temporary goes in.
As a public disclosure.
Yeah, exactly. So the next time I come around, what I do is I basically, when I come here, I basically get it out again. It's some very dumb. But you can keep tab of saying this is my temporary one, which is location here, and then what I do is now when I start generating this one, I basically get it back, move minus 24 out of RBP, sorry, RBP into R11, R10 or something like that. So it looks very dumb because you are saving the next instruction, you are restoring it. But when you try to go code generation, it will actually match nicely, and things become, optimization, things become easier. So here's what it is. So at the end of the day, what you will have is you will have operations like that in a flat list. So each of these X, Y, and Z should have very explicit locations somewhere. Some of them are temporaries. All three might be temporaries, but that means each has explicit location. Get from explicit location into R10, get from the explicit location into R11, do the operation, save. Okay. Don't worry, the actual next instruction I'm getting it again, just do the dumb thing. So at this point, we should be able to flatten out statements, do this thing. Okay. In fact, this is almost the same as my stack model. But the difference is now I actually have known handles for these temporary variables. In the stack model, is implicit that in fact there are temporaries in there. Here now because in some sense in your intermediate representation, instead of directly saying the temporary, if you associate a temporary variable name, then later on when you're optimizing, you actually have a temporary variable name, and you can deal with that separately. So why didn't I map all those things into registers? I could have said, look, I'm putting all my temporaries in registers. In fact, after optimizations, you could do that. The reason we didn't start here is registers are limited. If you have a very large, humongous expression, you might not have enough registers to do that. And so because of that, we don't want to assume that and try and do special cases when you run out of registers. Start in the general case and then do the optimization when needed. And in some cases, you might find there's no one-to-one correspondence between machine instruction and the decaf instruction you have. You might not find direct machine instruction. At that point, the best thing is to first lower decaf to sequence of instruction that actually has a corresponding machine instruction. And then you can actually go and do that. So at some point, when you look at the expression tree, it should have a matching instruction. Very inefficient. Don't worry. We'll deal with that later. And nice thing about this is you'll see you actually compile code getting faster and faster. Okay. The next thing we have to do after generating statements is generating control flow. So there are also two approaches to this. First is a template matching approach that we can actually easily do for decaf. And the second thing is a more algorithmic approach. So let me go through both. So template matching approach is for each construct. You have a very specific template, and we take the code and kind of plug it into these templates. And since there's not too many control constructs in decaf, you are not going to run make this problem is not going to blow on your face. So here's interesting. So if you have a statement like this, so the first thing you can do is write some code in assembly by hand and say, okay, so what should I generate? And then that will lead to a template. So the template is do the test, and if jump that the test is true, there's a label true, and do the false body and go to the end, and then do the label true. So this is, so basically in some sense, first is the false body, then is the true body, and the label end. So this is the way to look at that. So to give an example, so it's our previous code in here. So I want to look at first AX greater than BX. So I first do the, and I have a jump. So every time temple get instantiated, this shouldn't be the same label also. Some people make that mistake. So you have a nice template with label 0, 1, 2, and you get label 0, 1, 2 get instant. So you have to actually at least add the instance number into that thing. So it should be L0, 0, 1 or something like that. So, and also if you have descriptive names like that, it's easy to debug too. You know where it came from. It's not like some crazy labels showing up somewhere. So first thing you have to do is, I actually got those two variables out of using move queue. I actually added queue because I'm moving cardboard. It should figure this out automatically, but for some reason I made a mistake somewhere, and then if it thinks it's not a cardboard, it will actually complain than doing some weird intermediate numbers that you don't know what's going on. So actually, it's almost for my type. My type saved. I actually put this type in there, the cardboard type. And I did the comparison, and I'm doing a jump greater than to L0, which is the true body. And then I do the false body in here, which is basically, again, bringing A, X, bringing BX, doing the subtraction, and moving the result back. And then I will go do the true body, again, bringing BX, bringing AX, doing the subtraction, putting the result back. So very dumb. I mean, when I'm generating code, I don't know too much things. I only know is I have a map of each variable name and the offset from the base pointer where it is. That's all I need to know. And I generate code, I go to the next one. And there's no global knowledge, anything in here. And template for while loops is basically I do continue label, do the test, and do the body jump to the end and body jump to the end. Can I do better than this? Can I create more tighter code, tighter thing in here? So something like this. You can do test, basically, and a negative operation jump to the end. So in there. So you can play with all these templates and try to find a nice, cool template, do this, something like that. And now we go to do control flow. So, I mean, there's a thing. Do you have time? Yeah, we cannot have time. What do you think this should be? What's the best template? I'm trying to get people woken up so they can actually, instead of just listening, be active.
The body and then a conditional jump back up.
Into body. Okay.
Just like,
Yeah, so this is actually a pretty simple one. What you have is, where's the result? You have body, do the test, and jump to the beginning of that. So that's basically, it's a very simple simple template for that. Okay, that's the template model. So what you do is you hierarchically go down and basically keep plugging into the template. Another way to do that is create this control flow graph by expanding all the nodes. So I will leave this slide, I will get back to this later. Let me explain by example. So what happens is, if you have a function like this, condition if then else, you want to generate something like this that says, do the condition here, do the if part, else part, and exit in there, entry and exit. So that's the condition here. And then this actually gets into some very interesting issues. So for example, if program has this bunch of conditionals like this, ands and os, there's a notion called short circuiting. Short circuiting says, so assume I have and, the first condition is true, false, okay? I'm never going to execute anything else because I know that the entire and is always going to be false. Okay, so whereas same thing as if the first condition is true, so I know I don't have to execute the rest of the thing because it has to be true. I fall true. So this is why things like in C, sometimes in a condition, even if you put some statements that might never get executed because the first one basically dictates what happened, and I don't have to execute the rest of the things. Okay, so this is called short circuiting. So what that means is. So here's interesting. So if I have and here, you understand what's happening here? So I enter in there and do the first condition, I less than n, and in the first one here. And if that is false, I don't have to do anything else. I don't have to do the rest of the condition. I exit in here. And then if it is true, I go to the next one. I do that. And if it is false, I exit. If it is only true, then that's the only time I go and actually do this addition. So I do this condition twice. Same thing if I do this dual, if you do the O, because what happens is if the O is true any type, then I don't have to do that. I can just directly go and execute the body basically. And then you only false, go try the next one. And so if you have very large conditions, so you can do this thing, short circuit. So what you do is if you have complex control flow, you have this set of functions. You can go and deconstruct this complex control flow into a nice control flow graph where you have a body and basically very simple edges. So what that means is if you give some chunk of decaf code, we'll say n. At the end, what you'll do is you generate this control flow graph at the beginning and end. So, okay, you enter from the B node and execute, then exit from the N node, and between here, it's a graph instead of having these complex statements in here. So, and then there's a function called short circuit that says, given a condition, if the condition is true, goes in the true side, so it basically gives you a tree. So come in, do the condition, and go to two different edges. So you get edges, and what you do is you put together this to form a graph, and at some point you have to flatten the graph, and then if there's a contiguous edge, there's nothing in between, there is just control flow. If you jump over something, you have to generate the jump instructor branch instruction. In order to do that, you need to activate a new kind of node called a no-op node. So, simplest thing is, assume I have a sequence of blocks or sequence of statements, x followed by y. It's a very simple thing, put it into a graph. So, first thing what you do is when you deconstruct, deconstruct x. So, x could be anything. X could be complex, something like a while statement or some very complex structure out there. Who cares? But you deconstruct x, you get the graph out of there. To deconstruct a y, get the graph out of there, and then basically connect these two together. And then what you do is you return beginning and end this one. So you create this graph in here. So if you have if node, that means if condition xy, what you do is first deconstruct x, deconstruct y, and then what you do is to get the end, you put this no-op node and connect them together. No. And then what you do is short circuit the condition, do the condition for short circuiting and connect it here. So I will tell you how to generate this short circuit. So at this point, in this blob, each blob itself is a graph, and you connect together, you get a much higher graph, bigger graph. And then you return this beginning and the end node you put in there. While is also the same. So first of all, you create this no-op node to end it. And then you deconstruct the body, and you put a short circuiting in here. And now what do you have to connect? Where should the end connect to? EX, where should EX connect to? BC, yeah. EX should connect to BC because that's the while loop, and you return BC and E. So now what you have is again in the graph. And so short circuit, if we have a C1 and C2, basically you first find a short circuit for C2, and you find a short circuit for C1, and basically connect it like this. And so now what you do is return, we only had to return the beginning because T1, T2 get expanded in there. So this is the graph. Same kind of things for wire, just go too fast. So you put it. So and then what happens is instead of having this weird construct, you have a very nice flattened graph with these short circuit instructions as well as edges in there. So what you need to do is, so you have a graph, you have to flatten the graph. Linearly put the graph together, and you can do it in a down way or a little bit of a smart way, and then if there's edge that is adjacent going one to another, it's easy. There's nothing you need to do with this instruction followed by instruction. Any edge that has to jump over or go, something has to generate a jump instruction. So at that point you can generate code. Nice thing about this is now what you end up, other than in a template, is a graph. And then when you go into doing optimization, you can actually use this graph for doing a lot of analysis and morphing the graph. Because if you do template, now when you go to optimization, you don't have structure, you still have whiles, ifs, and stuff like that. And there's just no something nice, simple, uniform to analyze. This actually gives you something nice, simple, uniform to analyze. So this can help in the optimization. Even though right now it's a little bit harder than doing the templates. Just create this graph in there and then flatten the graph and generate code, and then later you can actually figure out how to morph the graph into different forms. Okay. I'm just going to jump over this. So another thing that will happen is when you generate something complicated like this, you end up having this no-op instructions. Not instructions, they are basically nodes in the graph. And so you can do very simple optimization, saying if you have a bunch of things coming in no going out, you can directly connect them. You don't want to keep generating nodes. So you can do one simple optimization even now and do that. And then you need to come up with a little bit of an intelligent way of flattening the graph. You can just randomly flatten and then everything will be a branch. Every instruction probably have to jump, but if you flatten it a little bit more intelligently, you can eliminate the amount of branches, jumps you do. So actually I told you a little bit. So what do you think pros and cons of template versus matching versus algorithm? What would you guys use? If you have 1 minute to decide, would you use template matching or algorithm?
Well, it seems like the template matching is a lot easier to implement quickly. With the algorithm one, it gives you more information. So it would be more useful for optimization later.
See, what happens is if you do template matching now, you probably do the algorithmic approach when you go to data flow optimization. Because suddenly when you do data flow, you say, geez, now I have to write data flow classes to deal with all these weird constructs. And data flow basically has a notion that the control comes into some place, join and split, and you iterate through this graph. It's nice to have a graph of a while. How to iterate data flow through a while if it's going to be much more complicated? And so you need to have all these weird high level things. So if you have a graph, it becomes much more easy. So I mean, it depends on where you want to buy the bullet. You want to buy it now or later. So at some point, I mean, template might sound very interesting anything, but later it might help to have the graph constructed. Anything you guys? Anyone want to add? Okay, so I want to give a little bit of flavor of this x86-64 processor. How many of you knew about this before we assigned in the class? Did everybody knew, have followed up all the epic battles between Intel and AMD that led to this point? Okay, so x86-64 is a CISC architecture versus what we call RISC. In 80s, the big thing was reduced instruction set architecture for RISC. It's supposed to be the in thing. It's a much nicer, simpler architecture, can do a lot of cool things, and everybody thought it's going to take over the world. Technically, it should have taken over the world. Obviously, a lot of times what happens at the end is nothing, only small percentage technical, a lot to do with business, a lot of other things. Intel did a really good execution and managed to keep this clunky old x86 going. So it has a very low lineage. It's 80, there are 8-bit instructions, 16-bit, then they become 32-bit. So still, if you look at the instruction set, I said the manual is this thick, and there are things that probably still can date back to 70s. A lot of old decisions still stuck there. And so this worked out really nicely for Intel. It actually went from Pentium to kill all the other RISC processors. And then there was a shift to 64-bit. So 32-bit was running out. What's the problem with 32-bit?
So, for virtual memory?
Yeah, 4 gigs as the maximum you can allocate access is 4 gigs, and you want to go beyond that. You want to have larger programs, and so you can do crazy things like have multiple things getting premium, or what you like to have is a nice large address space. So it's the first time after all these years, after killing all those RISC architecture, Intel made a strategic mistake. What they did was they came up with a complete new architecture called Itanium. I said, this is our 64-bit architecture. If anybody wants to do 64-bit scientific computation, do Itanium. x86 will stay 32-bit. And they were trying to go with this dual architecture, so hoping that Itanium will someday take over x86. Itanium was a lot more in the RISC class architecture. In fact, I can go forever. They took a RISC architecture and make it look like CISC, so they actually kind of ruined the architecture a little bit. But other than that, so they started going in that direction. Except then AMD came out and said, wait a minute, we don't want to do this Itanium. We will basically expand x86 to do 64-bit. And they came up with this thing called x86 64, and at some point it get popular enough that Intel had to backtrack and start supporting it. So this is the first time Intel actually didn't have in the lead. So what it did is, so how does architectures keep expanding at it? So what these architectures do is they have different execution mode. So it's like having multiple chips on a single processor. So you have the x86 mode, and then there's the 64-bit mode that basically gives you all 64-bit registers. They change the register name a little bit. And plus, they actually added additional registers. So that's why we picked this up, not because it's 64-bit, but because instead of having 8 registers to deal with, now it actually has 16 registers. So we have more registers, so we can do register allocation and stuff like that. So this, and it also, at 64-bit, things become uniform when you go to larger levels, but I don't think you guys are worried about that we don't write huge programs. So this is the architecture we are working on. So if you look at AMD Athlon and all those machines are 64-bit. The new Intel Extreme, whatever, it's not just Extreme, it's hard to figure out what Intel architectures these days has 64-bit. And still, a lot of operating systems also are not 64-bit, so Windows is still not 64-bit supported. In Linux also, since these machines can run 32-bit too, a lot of times you run 32-bit on even the process 64-bit. So the machine we got is actually supports a 64-bit OS, so you can actually run native 64-bit. And you need to provide everybody with the passwords. Okay. And the key thing about the machine is it's new. It's already crashed once. So what that means is if it hangs, don't wait, call somebody, send email to either him or me, and we'll try to figure out how to go and remove the damn thing. Because everybody's using that machine. And if everything fails, it's file mount is a problem. Everybody has local disk, so you won't mount anything else. You can use everything to go. So we'll see. It's still a fairly new experiment. So interesting to do is we are using this one processor. But there are a lot of other different types of processors. Each has its own idiosyncrasies, a lot of interesting differences. So all these other processors here in listed are basically RISC processors. And another very interesting class of process happening these days are signal processing, digital signal processing process that deals with that's like every one of your cell phones and everything probably has one of these DSPs in there. And in higher end, there are things like supercomputers that still have to be code generated. And then also with the lowest end, things like fire alarm up there and stuff like that have this embedded process, very simple 10-sense processors that you can get. In fact, there are these greeting cards when you open it to sing that has a processor in there. It's probably very simple processor, probably costs 10 cents. And then there's network process and stuff like that. So interesting thing is we are learning to do code generation for one, but a lot of these processes have commonalities, but some of them, the important fact is very different, what you're worrying about. And each of these processes have very different types of execution. For example, it's a class called BLNW. The itanium processor was in this class. It is, instead of giving one instruction at a time, you give this very long instruction. When you execute it, it will do 8 different things in one clock cycle. And x86 is a class called superscalar, where you give simple instruction, but the hardware will rearrange them to run them faster. And there are vectors, there are a lot of different types of things. Each of these has different memory system. For example, all the things we use has this very nice, large, uniform memory system. But things like DSPs don't have cached, nice memory system. It has specific limited size memory, and it has multiple of them. So you have to manage memory systems like you're managing registers. And in something like Spark has this notion of a register window, because what it says is, so we have registers, we'll say 1 to 32, and the first registers in function call, when you do the function call, appears as the last registers of the next function. So you have register window kind of moving down. So if you want parameter pass, you just allocate it to first set of registers, the function call, it appears as the last set of registers previously. The interesting thing about that is, so its hardware manages register windows, so at some point if you do too many function calls, the hardware will stop and has to take all these things and put it into memory. So it provides some speed, but if you do too many small function calls, it actually becomes a bad thing, because even though if you don't use all the registers, it has to keep all the registers running. A lot of interesting things in there. And every instruction set architecture is very unique. And also another thing, when you do optimization, there are a lot of different calls. When we do optimization, we look at performance. We try to run things faster. But there's a large class of things these days. Fast is not the most important. If you have your cell phone, what matters is the battery life. So how do you run your cell phone codec with the minimum amount of battery life? And that addresses a very interesting different class of optimizations. So at some point when you do optimizations, depending on what you look at, there's a very large class of interesting things you can do around this. Okay, that's my digression into architecture. So what we have done today is we are here. I think anything and everything you need to know about generating code, I think we have covered. If I haven't covered anything, send me here. So I want to give you a few guidelines how to do this. First thing is, when you are going through, now you have abstraction level that actually is a correct program. Okay? One thing to do is you can do this crazy reorganization that at the end start producing correct program. That's not a good thing to do. What you want to do is you can write this next layer multiple passes. Each pass lower some part of things, expand the control flow graph, expand into expression tree to tree address form, but at the end of that still have a correct program. The reason I'm saying that is when you look at optimization, you might find one of those places might be the best place to do your optimization. So if it is correct program and everything is working, then you can basically plug your optimization from in the middle. It's easy to debug too. So if a lot of times if you have correct program, you can look at this thing, okay, look, this program has to be correct, what's wrong with it if something goes wrong. Then saying, okay, I am munging too much. In the same way, don't try to do too many things at one pass. And programs are complicated and sometimes debugging is a nightmare. But each pass do something simple. It's going to be very inefficient. Don't care. We don't look at your compile time. Just do any inefficient thing. You can do a lot of refactoring. Use the same code base, but do small things at a time. If you want later, compile them, but just do slowly build it up. And yeah, again, I to that. Always keep the correct semantics. And a lot of times in compilers, there are so many hidden things that goes wrong. Anytime if you make a decision, especially you are doing good assertions, everywhere if you make an assumption that what the graph should look like, what you expect, you just assert. Because one of these days, between now and code generation, you will forget what you did, and something goes wrong, and you'd rather catch it from assert than debug for hours trying to figure out what went wrong. So just put assertions all over the place. It's always good practice to do that. And this is hard to say because sometimes when you generate this code, it's painful to look at. You look at that and say, darn, I am saving this in previous instruction, I am loading in the next instruction, I am adding 0 to this. What's the deal? I can easily just add just one line of code and get rid of it. It's just so it's painful when you look at some of this, but just do that. Because that you can do it optimization, you can get a lot of satisfaction by doing all those things optimization, but now don't try to do any of those things. Just generate simplest thing in there, and that's why when you do optimization, we can do comprehensive thing there, just simple people things that you can do. And this is not that important these days, because if you are generating things like object-oriented type code, there are things you can actually do in runtime. So assume you're allocating some memory, you will do a bunch of instructions again and again, you don't want to generate them, you can write a small function, put it in a runtime library and call it. It's much easier than trying to generate that, because it's easy to modify, you easily do things like that. So always figure out what you want to generate and what you can actually stack off in the runtime system. Key thing, we are doing optimization later. Let it do the optimization. And one thing you need to do is right now think about optimization. Because this is one thing that's really hard about this course. Because normally in a lot of places where they do compile code, what you do is you get the entire template and you say, trust me, use this template. Because at some point you will actually need it. And you have no idea why that is, and you go fill in the blanks and build a compiler, and then you have really nice working compiler. But you have never learned why you actually made those decisions. What you do is we give you a lot of rope that you can actually hang yourself, because we don't give you any kind of guidelines, and you can do, and every class at some point in a later project they're going to scratch and say, damn, we did this thing, and that we are going to redo everything from like early on. That happens to everybody. But that's the learning experience, because you know that you'll never ever do that mistake again, but you have to recover from that. So what that means is, if you are doing some of these things, just think a little bit about optimization. Just ask somebody, ask Punya what's optimization like, and then because you need to have that feel, because since the optimization projects are also 3 weeks, you don't have time to rewrite the compiler. So the key thing is even though you don't know what it's going to be, you have to actually be ready for it to coming. And key thing is sometimes you might have to do things that are not the most intuitive things, like I talked about how to map control flow. There are some easy, simple things you can do today, but later you'll worry about. So design decisions, talk to Punya and say, these are the decisions I'm making. And then ask, okay, what's my consequences? What do I have to pay later? Is this a great thing, or am I going to run into problems? And then some of those things might be subtle, like things like temporary variables. And you can do some really cool, very simple things of doing better temporaries. But later you might, when you do code generation, you say, wait a minute, now I did this thing, and now I had to do this very crazy analysis to figure out that this weird thing is going on. I mean, key thing is understanding all those things. Another thing, a lot of people found out, good teams is, they create, actually there was some teams that when we used to let, even 3 people teams, some person did a huge concentration on doing things like build and regressions. Didn't do that much code generation.
My team had that.
Yeah. So one person basically spent all this time just building regression tests at every level, just go and testing these things. And yes, it reduced the amount of people we have to do the real code, the implementation, but it can actually really simplify your life when you're trying to debug. The debugging compiler is a nightmare. The best thing that compiler can do is actually crash. Because when the compiler crashes, you know where it crashed, you actually get the debugger. If it produces bad code, how are you going to debug that? Because somewhere, someplace that it misplaced something, a variable, something, and now it's the compiled code is crashing once in a while. And that can become a nightmare. Because you have no idea why it's crashing. And it's something that if you have 50 parsers at some point, 20 parsers, one of those parsers did a strong transformation. Some of them doesn't even show up till later, because it did the conceptual wrong thing that later parse actually did the right thing, but the assumption was wrong. And this becomes a nightmare to deal with. So it's writing a lot of test cases is actually a good thing. So I think putting some time into that can really save that last midnight for you guys. And a lot of times bug hunting is doing a bunch of bind research. When you have this interchangeable and switch-offable parsers, you can bind research through parsers, bind research to procedures, and at some point something will just pop up and then so this is debugging this. And other thing, finally, checkpoint. Take this seriously. Think this as a deadline and really work for that deadline. And then you can take a breather and then have another deadline coming up for turning things in. because this is a large project. A lot of things need to be done. So due date is there. And finally, some of the guys have paper reading tray with me, and the other group has marked on Friday. Okay, good. Don't get frustrated. If something goes wrong, especially with the machine, immediately send email. Okay, so you need to be up. Make sure that keeps up.